This is video help for problem 27.2. I'll rely on the fact that the formulas that are in the text and in some of the formula calculations are indicated in the written homework. Hence, I'll try to tell what this is all about and with some overview of the mathematics here. We've got three coaxial loops, one in the center, two symmetric on the side, and we're trying to make the magnetic field uniform in as big a region as we can in the center. We want homogeneity in the middle, around z equals 0. So the neat thing is we can just kill the higher order terms in z to the nth in any Taylor series expansion along the z-axis, because Maxwell will guarantee that then it'll be uniform off-axis in a comparable distance. And so it is, that Helmholtz corresponds to, drop that middle loop, gives us a nice homogeneous field if the radius of these two guys is twice z0, that is equal to the distance between them. That will kill the z-squared term. You'll just have the constant term. The odd terms all cancel out by symmetry, and you really get something really nice and uniform. Look at this. Here in figure 27.5, you see how nicely uniform this is, and that will be uniform then in the transverse direction over a comparable distance. So, what we're going to do is we're going to try to do this again now with this middle loop. That is, we start over. The expansion is easy for this guy. You just specialize our formula that we've gotten along the axis by putting s equals 0. And the parameter there is an offset for the coil. And then we use the alpha freedom in this current to kill the z-squared instead of the z0 freedom. It's arbitrary z0. Then, by the way, you could adjust z0 and b to kill z to the fourth, but we don't ask for that. We just say go back and kill z-squared in a different way from the way you killed it for Helmholtz in the text. But caution, here's what's going to happen. If you do this, and then you try to use z0 freedom to kill the next term, say you get even super uniformity, z to the fourth, you might find z0 getting smaller than a half a, and then alpha would have to be negative for the cancellation to occur that you are calculating. And that is a problem, because then if this is a negative current, then for a given current here, you won't get as strong a B field in the center. And so you'll lose field strength. But that's not specifically what we're asked to calculate. On the other hand, we are asking you to think about that. Finally, just keep in mind two wonderful things. Throw away the middle loop, and the Helmholtz pair are sort of a first approximation for your RF coils when you want to make a uniform field perpendicular to the main magnetic field. Put the loop in and in fact make bundles to kill higher orders, fourth, sixth, eighth. They try to get it down to uniformity in parts per million over DSV, diameter, spherical volume, your imaging volume you're interested in. And that's those bundles that you see in the other discussion in this chapter.